So assignment 17. Okay, so that assignment 17 that we had from last night, that will be collected on Tuesday. So remember I talked about there's some zero periods that we'll need. I definitely want to have zero period on Tuesday. So that means Monday we don't have class. You can come see me Monday at bonus. I can answer general questions about topics. So if you come to me and you have like a general question, I can help you. But obviously it's a quiz, so I can't like do specifics. Does that make sense, Mayan?
If we create another version of the question,
sure. You can do that. So if you come up with your own question and maybe it's a similar question, I can help you with that.
You just change one constant, the derivative will be
because that's
exactly
kind of like you're making your own practice quiz,
Oh,
right?
sure, yeah.
So of course I think making your own practice quiz. Well, that's what Mayan's saying. Can she come to me at bonus with a similar question that she made up on a practice quiz? Yeah. Okay. So back to. Let me just recap, because there was a lot of information yesterday. Let's just recap what we did. And those of you that weren't here and didn't have a chance to watch the screencast, it's on MyJag. You can watch it later. So we did the first derivative test. This was technically all review from the previous lesson, right? The whole finding the derivative, the critical points, increasing, decreasing, and then we located maximum and minimums. Okay, then we did the new part, which was the concavity, which had to do with the second derivative, right? And we established when the second derivative was greater than 0, we made a little kind of smiley face, right? Concave up, and then when it was negative, sad face, right? Concave down. And then we did these examples, right? So we still did a number line, but remember we didn't make the little arrows. We did little kind of like parabolas up and down. Okay, this was, I believe, and then we also did the points of inflection, which is where the concavity changed. And how do we find the actual points of inflection? We plugged back into the original function. Griffin.
So there were, on the homework, there were problems like this, like that, like gave you an equation like that and asked you to find the point of inflection. Don't you don't have to do the number line, right, when you're just finding the point of inflection?
Well, I do the number line for the second derivative to see where it switches from negative to positive or positive to negative.
Are you saying multiplicity wise?
Well, no, I'm saying like you could find the critical points and then just plug them right back in to find the points of inflection, right?
Yes, but here's where I want you to be careful. There are scenarios where it could be negative. And then in that case, 0 would not have a point of inflection.
Okay.
Yeah, so just because you get values where it's equal to 0 or undefined, it doesn't mean they're necessarily going to be a point of inflection, because you can have a graph that is concave up and then stays concave up. Yeah, I mean, you could have, it would look probably, I mean, there's a number of different places. It could even be like a piecewise function or something, right? I could have like, right, that's concave up, stays concave up, so there's no point of inflection. There could be a critical point, and there's a minimum, or a maximum actually in that case, a local maximum, but it doesn't have change in concavity. Okay, then we did looking at the original graph and trying to figure out on what intervals was the derivative equal to 0, where was it positive or was it negative, so we looked at the slope, right, increasing, decreasing, and then the second derivative, concave up, where it makes like, right, that upward, and then concave down. And then I said to approximate, to find the estimate where the point of inflection, we kind of find like that middle point, that midpoint. Okay, on to example 5. Now, last one, I gave you the graph of the original function. In this example, it's a picture of the derivative graph. Okay, so I'm not giving you the original. So we want to find out, so for part A, for the original function, where is it increasing? And then for B, we'll find out where is it decreasing. and then estimate the x coordinates for all the local extreme values. All right, well, take a look at this graph. If I were, you don't have to do this, but let's say I made a number line here, and I said that's f prime. Now imagine, right, these arrows, or I'm going to throw in some arrows here, it's going up, but we know it's going all the way from negative infinity and then all the way to the right to positive infinity. Okay. Okay, now, if I'm looking for places where f prime is equal to 0, where is f prime equal to 0? Where it crosses. Okay, so that's going to be at -1 and 3. Right, it's crossing right here, if you want to look. So it's where f prime is, because remember, this is f prime. This is the derivative graph.
Well, that technically is the slope.
So
Wait, so
Yeah.
if this was
Where the slope is.
if this was just f of x,
Because it's a
would it be
derivative graph.
where the slope is 0?
right, let's say this was the original graph. Where do I have the derivative equal to? It would be here and here and here. Okay, horizontal tangents are where it's undefined. But now I'm looking, I want to interpret the actual derivative graph, because what happens on a lot of the multiple choice or FRQs, you might have the original graph, you might have the first derivative graph, you might have
Bless you.
the second derivative graph. Bless you.
Thank you.
And then you have to know how to interpret it, okay? All right, from negative infinity to -1, is the graph positive or negative? Is it above the x-axis or below the x-axis? Is basically what it's above, so it's going to be positive. And then from -1 to 3, it's all below the x-axis. And then from 3 on, it's positive. Okay, so we made a number line graph for our first derivative. Can I put the little arrows in if I want? Increase, decrease, increase. So we just took the actual graph to interpret our number line. That means I know, what do we have? A max at -1 and a min at 3. So if I go back to the original function, let's think about this. Anytime it went from above the x-axis to below the x-axis, it went from positive to negative, there's a maximum there.
I thought we were finding where it's going.
We are, but what's the little pluses? Isn't this
That's
where it's
where it's
increasing? So anytime it's above the x-axis, the derivative graph, it's increasing. So it's going to increase from negative infinity to -1, union. There we got that union again. 3 to,
I was thinking about that.
So
Did you know
funny.
it was you?
Yes, I did. I
How?
heard, because I knew Miss Malikian said it one time.
No one-
and
well, no
I,
one
every
knows
time I
how
Yeah.
write it, I say it in my
No one.
head.
Oh,
No,
what?
Abby is in my office.
okay. Where is the graph decreasing?
I learned it at my old school. Oh yeah.
-1 to 3. So, again, I don't have enough information to determine any y values, which is why, I don't know if you've noticed, often I'll stress more about what the x value, where it's located, than what the actual value is. So we're going to say, where's the local values? So we have a maximum, and you don't have to write local. I think I mentioned that earlier. Just put max. Only if it's only if I'm asking for the absolute maximum do we have to specify that. You'll see on the take home, I actually write it out. I'll say like absolute.
Chris and I were talking about this. Did we ever get a specific thing that says like how to identify when it's
I was
absolute?
absolutely because there sometimes when
Isn't it like each hard to tell?
Yeah, I think so, but on the homework it asks for the absolute.
Yeah.
It says to use the first test, the first derivative test.
Yeah.
So I don't know how to find the absolute if I'm using the first derivative.
Oh, so okay, just real quickly, when we did the first derivative test at the beginning of the lesson, in an example like this one, this is an x to the third power. this is not going to have a absolute maximum or an absolute minimum, because we should be able to recognize what's a cubic function look like. So we have, these are both relative or local max mins. However, if we had, and in this case also, we have the same kind of situation, what we would want to consider is if you have endpoints. And if you have, like, right, so you can actually, it all depends on the domain.
So like you can't have absolute
Well, you
or minimum with negative infinity.
You can. Okay, so be careful there.
'Cause some-
Let's take a parabola, for example. A parabola
Oh yeah.
has an absolute minimum,
Yeah.
but not an absolute maximum.
Do we have to know what the graphs look like? Because I know it's somewhat.
Not exactly. Some of them you should. You should recognize a cubic or a quadratic.
But I think some of them were like rational functions, and they were asking like absolute.
Well, then I guess they would have had endpoints, right?
Yeah, they-
I know what problem it is. They did have endpoints.
They had endpoints.
And then after that, you just see for the absolute max, just the biggest number.
was number 5.
Okay, we'll tackle that once we finish. Are we good with this one?
Yeah.
Okay, excellent. Okay, we have a second derivative test for local extrema. Okay, so here's basically what we're saying. Take something like f of x equals negative x squared. I'll just kind of walk you through and then I'll explain what it means. If I do the derivative, what do we get? Negative 2x. So I have a critical point where? At 0. Now, if I do the second derivative, I get negative 2. Now, that implies that the second derivative of 0, well, it has to be negative 2. So in other words, it's negative no matter what I plug in. So what we're saying, and kind of, you can think of this visually, what does negative x squared look like? Looks like that, right? It's concave down.
Yeah.
And at that critical point, so if it's so what are we saying with this part? At 0, it's a critical point, so we know it has to be a maximum or a minimum, and it's concave down, so I know it has to look like that. So if I know that I have a maximum and it's concave down, right? So basically what we're saying is if you have a critical point and the second derivative is less than 0, you have a local maximum there. Okay, so it's kind of just working backwards. Does that make sense? And then just the opposite happens in this one. So if we have a critical point, right, that's equal to 0, that means we have a horizontal tangent, in other words, a maximum or a minimum. And if the second derivative is greater than 0, then we have a local maximum. So kind of the same idea. We do the first derivative, we get 2x, which implies that we have a critical point at x equals 0. It's just the exact opposite, right? Second derivative, just a minute, Ryan. And it's going to give us 2. So that implies that the second derivative at 0 is 2. So again, this tells us that we have a horizontal tangent at 0. Right? We have a horizontal tangent and it's concave up, so that means this has to be a minimum. No, just the fact that we got positive. Like I could give you another example. Somebody.
Why does the one on top not have a horizontal asymptote?
Oh, it does. Sorry.
Okay.
Sorry, I just didn't specify it.
Okay.
Yeah, right.
Does this not apply if like the f prime of c doesn't equal 0? Or does it still apply?
What do you mean?
Like, is the f prime of c in both?
Right. F prime of, so when we solve, we get 0, and so the derivative is 0. And so when we plug in the second derivative, we get negative, so it has to be concave down. Basically, here's what you're doing. You're basically determining, do we have a horizontal tangent, a critical point? Do we have a critical point? And then at that critical point, is it concave up or concave down? that will tell us if it's a maximum or a minimum. So here, just a quick example. Let's say I have some function and we don't care what it is, but let's say the first derivative at 2 is equal to 0, and I tell you the second derivative at 2 is -4. So does that mean at 2, is it concave up, concave down? Is it going to have a max or a min? So this implies f of 2 is a maximum. That's essentially how that works.
Because the first derivative was positive.
Right, so this tells us that we have a maximum or a minimum. Like this tells us it's a critical point, right? And then this tells us it's concave down. So if it's got a horizontal tangent and it's concave down, then there has to be a maximum point. Yeah.
Now let's just get to an example.
I'm confused. I got
Okay.
confused. Sometimes the examples help with my.
Yeah. Or is this
Okay.
gonna make it worse?
No.
No, I just got confused with the last thing.
Okay, well, I'm going to do that here. Here's an example. Okay, Ryan, you had a question?
Yeah, like, what if it was like f prime of x equals 1/2? 1 is 2 is the second derivative, then the final equals 0, so
No. The derivative has to be equal to 0.
oh, in order to use this?
Yeah.
Oh,
Because, okay, go back to this. Right? Like, look back at this one. Where was f prime equal to 0 on here? Where you had horizontal tangents. So let's take this one, for example. Here we have a horizontal tangent at 0, and it's concave down, so I know that's a maximum. Here we have a horizontal tangent, and it's concave up, so I know that has to be a minimum. We just didn't think of it that way. We didn't think of it in terms of concavity. We just looked at the graph and was like, oh yeah, that's a maximum, that's a minimum. But sometimes, as you can see in this next example, do I have a graph? No, I just have a bunch of values. Okay, so we want to find any local extreme values for this function. Okay. Yes. All right.
There are endpoints.
So
Yeah.
what do we want to consider first? Well, we can only consider what values we have. F of 5 equals 0. Why is that important?
Because it's a 0, so there's gonna be a
Is that important?
tangent.
Okay, f of 2. So let's just look at, so we have two basically values here. We have 2, 5, and 5, 0. Okay, then what else do we know? We know f prime of 2, oops. We know f prime of 2 is 0 and f prime of 6, or sorry, f prime of 5 is 6. And then we have second derivative. So this is kind of, remember on that last example on the bonus question, I just gave you a bunch of different values. You have to decide what is important here. Okay, let me go back to this example that I kind of scribbled up here. What's the first thing that we want to have? We want to have a derivative equal to 0.
Then, you know, it's
Okay,
like-
which one has a derivative equal to 0? Okay, right there. Okay, that tells me I have a horizontal tangent, basically. Now, f of 5 equals 0, that's great. That just means it's touching the x-axis there. Does it tell us any information? F of 2 equals 5, that's just a point. Okay, now what else do I need to know? So in this example, I said I wanted to look at where does it have a horizontal tangent, and then what's the concavity at that same value?
down.
Ah, right here. Oops, sorry, I thought my highlighter was still on. Here we go. So since f prime of 2 equals 0 and f double prime of 2 is less than 0, okay, so what do we have? We have a horizontal tangent and it's concave down. Therefore, that has to be, so at x equals 2, we have a maximum. So just like that bonus question where I gave you a bunch of extra information, this also had extra information. You have to establish what's the important parts here. Okay, so first figure out where does the derivative equal to 0. Then look at what's the second derivative at that same x value to see if it's concave up or concave down. Nisha?
So do you know if anything with the f prime of 5 because it doesn't equal to 0?
Doesn't. So f prime of f double prime or f prime of 6? Oh, this just tells us that it's. This one just tells us it has it's increasing at.
If you get the f double prime equals 0, that doesn't tell you that it's concave up or down.
No, this could be a point of inflection, but we don't have enough information.
Okay.
Because remember, when the second derivative is equal to 0, if the concavity changes, then it's going to be a point of inflection. Technically, when the second derivative is equal to 0, it's not concave up or down.
It's just like there.
Yeah, so it could change concavity there. We don't know. Okay,
But does it even exist on the graph though?
it could.
Like a derivative of x is 1, and then the second derivative of 1 is 0. So yeah. How would that graph?
What do you mean?
Like if the first derivative of like x is 1, and the second derivative of 1 is 0, how do you graph that?
It wouldn't have. Sometimes it doesn't have concavity. Like if it's a line, it doesn't have. Like just take y equals mx plus b. That has no concavity. So that could also occur. Okay, here we go. What do we want to look at first? What was the first thing? The first derivative when it was equal to 0.
At 1.
At 1. So I'm going to write this out so we have it all like the previous one. So f prime of 1 was equal to 0. Are there any other places where? No.
What up? Is the
Double prime.
DNE,
One.
Alright, so b
doesn't
double
that,
prime
can that
equals
also be a
negative 1.
critical point? Or would that
So-
be undefined, or is there a difference?
So when we're doing the second derivative, we're just, we're looking for where it's equal to 0.
Not undefined.
Not undefined. Yeah. Mainly because if you think of like a corner or like a cusp is concave down, and it's undefined at that point. So we want when it's equal to 0.
Which means it would just have to be a constant, though.
Yeah, and then we want to look at the second derivative of 1 is negative 1.
So we have a maximum. I understand those cases.
Okay, so that means we have a horizontal tangent and it's concave down, so that means, right, so therefore, you could say it has a maximum at 1, or you could say f of 1 is a maximum. I'm okay with either one. X equals 1 is fine, because that's how I said the last one. Either one. Okay, last example. We're going to put it all together.
Yay!
That makes it any better.
You don't know if it makes, no? Okay, well, what did I give you? I gave you a derivative. So if I gave you so I think you might have had a homework problem or 2 problems like this. Did you?
I didn't do it yet. Probably didn't.
Okay. If I gave you the derivative, I don't have to do the derivative in order to find the extreme values, do I? Yeah, so first of all, let's just write out the domain, which is negative infinity to infinity as a reminder. Also, look at what kind of function it is. It's a cubic, so it makes sense. Okay, we also want to see where it's increasing, decreasing. We want to see concave up, concave down, and then we're going to sketch a possible graph for the original function. Okay, I know. Actually, I'm going to not put A in first. I'm actually going to do all the work first, and then we'll answer all the questions. It's actually easier. So if we have f prime of x, I don't want to do the derivative for parts A and B. I just want to factor and set it equal to 0. Because that first step is, kind of envision that first step is already done for us. So what can we factor out? 4x squared, and we get x minus 3. So I have critical points. Good, 0 and 3. So let's make a number line. for f prime. Negative infinity to infinity, and we want to put 0 and 3. Okay, I don't know. Let's plug in something less than 0. Negative 1, so squared, that'll be positive, negative, so negative. Notice that multiplicity of x squared.
Oh, so it's gonna be negative on the next one.
Yeah, what if I plug in 1?
It is negative.
It is negative.
Oh,
Good.
that's crazy.
Okay, so that can happen. That's why it's good to check. And then obviously bigger than 3.
Concave down, like can I have both of them?
Okay, so now keep in mind,
Concave,
is
though.
this increasing, decreasing? This is the first derivative.
Oh.
So it's going to go decreasing, continue to decrease, and then it's increasing.
So that other one is negative.
Okay, so now I can answer A and B. Okay, let's interpret where we have extreme values. If it's going from negative infinity, I'm not going to have a max. If this was an endpoint here, this would be a maximum,
Yeah.
right? But it keeps decreasing. Nothing happens at 0. It stays decreasing.
3.
So until we get to 3. So we have a minimum. So we have a minimum at x equals 3. Or you could write min is, there's a min at f of 3 or something like that. Okay, for part,
Sorry, is that like an extreme minimum or a local minimum? Just as extreme though.
Extrema doesn't necessarily mean it has to be the absolute.
Okay.
It just means in general.
right.
You would specify if it had to be.
It's funny though, because it says extreme.
Extrema, right. So we're talking local extreme. Extrema is just plural for extremes, right? Local max. Don't worry about identifying the absolute maximum or minimum unless I tell you. If I just say this, just write max and mins. Don't worry about establishing if it's the highest or the lowest. Yeah, that's fine. Okay, now we want to find increasing and decreasing, which we've already done the work for, right?
How come you don't find the y? Like, why aren't you doing f of 3?
Okay, so do we know what f of x is equal to? We don't. So that's why it's all about where.
Why can't you like assume that it was like x to?
Okay, so what we're going to work on, so first half of calculus are derivatives. Second part of calculus are integrals. That's where we work backwards from a derivative to find the original function. Okay? We do not have enough information, even if I taught you integrals, we don't have enough information to find the original function. We can find out what it looks like, but we don't know exactly where it's located. Why? Why? There could have,
Yes, Abby.
she got it. There could be a constant. So think about when you do,
Oh, because you just get rid of it.
what happens when you do the derivative of a constant? It goes away.
It goes away.
Do we have any idea what that constant might be? Very good.
That was good.
Don't care.
Okay.
Wait, so there's a way to figure that out?
No, not a bad.
I was going to say, ooh. Okay. Oh, got it. Okay, so, all right, decreasing. Now, don't stop at 0.
3.
Okay? If 0 was something we were excluding from the domain, you understand what I mean by that, right? Like if there was a removable discontinuity or an asymptote or something. But no, we don't have any of that, so we just write negative infinity to 3.
Why exactly are there brackets around?
Okay, so technically, so the way calculus defines it is it increases right until we get to 3. We include that endpoint. The College Board will allow parentheses for this because there is very few, but there are some calculus books out there that will put parentheses instead of brackets. So I stick with what the majority of calculus textbooks do, and they put brackets. Concavity is all parentheses, though, which is what we're going to do next. So now for C. Okay, so now we're just going from here. That derivative is going to be what? 12x squared. Good. And let's factor it first before we put it equal to 0. So I can factor out a 12x. And then we have an x minus 2. So we have two possibilities for points of inflection, which I didn't ask for here, but x equals 0 and 2. And what do you think? Are both of those going to be changes in concavity? Yeah, because look, these are both to the first power. If one of these was squared, like we saw in that previous one.
Oh.
All right, remember, it all comes down to the multiplicity as to whether it crosses or not. So now I'm going to label. I'm really particular about these labeling.
Like you'll take a point off.
No, I'm always particular when I'm teaching it because it can be confusing when you're in the middle of a problem thinking back, wait, what am I plugging into? Am I plugging into the original, the first derivative, the second derivative? So that's why I'm always, if you forget to put it on your test, it's okay. That's why I just keep saying it because I don't want you to forget.
I'm gonna hear your voice.
Don't forget. Label your line graph. Okay. So we plug in -1, positive, good. And then plug in +1, negative, and then positive. So I'm going to put my little smiley face or sad face. So smiley, sad, smiley. So it's going to be concave up, -infinity to 0. Okay, don't include the 0. And then 2 to infinity. Okay, and then concave down will just be 0 to 2. Okay, last thing, we want to try to draw a graph of the original. Yeah, Molly, you had a question?
Like the regular function? No.
She had her hand up, sorry. The original function.
Why don't we do 0? Yeah.
Because you can't have something concave, because technically at 0, it would be a point of inflection.
Oh, got it.
Right? So where it switches, we don't count. Thank you. All right, now we want to draw, I'm going to just make like an x-axis here. I'm not going to make a y-axis. And we had just mentioned y. We don't know what the original graph looks like. I don't know where on the y-axis it's going to go. But I can label what are some important features of this graph. I had stuff going on at 3, 0, and 2, right? At 3, there was a minimum.
And it goes like,
Yeah, so here's what I'm going to do. I'm going to put 0, 2, 3. I'll put 3 close to the 2. Okay. Now, imagine this is, okay, so here's what we want. The graph is going to start from the top. It's going to decrease and stay concave up. So just kind of picture, maybe I can put it on the board. Decrease and concave up until we get to 0. And then what happens at 0? It's still decreasing.
wait, would decrease but concave up?
Okay, decrease, but concave up is like that.
That makes no sense.
Oh.
All right?
And if it was,
Right? This is decrease, concave up.
this is increase concave down.
Okay.
It's a rainbow.
Now it's going to decrease. It's going to continue to decrease, but now it's going to become concave down.
Where?
Right here is 0.
Why are you like doing
Oh, sorry. Because I just wanted to take it like piece by piece. Okay, I'm on it, Molly. Okay. So I'm going to just draw it from here. So here I go. There's to 0. Okay? Then what do I want to do? I want to make it concave down and decreasing until I get to 3. Oh, well, I'm still decreasing until I get to 3. You're right. It's going to be concave down to 2. And then at 2, it becomes concave up. 3 is a minimum. And then it goes up. So it's kind of like, it's hard to draw all at once or in pieces. It goes concave up. 0 is a point of inflection. Concave down, but it's continuing to decrease. then it becomes concave up, still decreasing until we get to a minimum, and then it increases. Kind of a crazy graph there, huh? Okay,